today I'll talk about Deepfool paper. It's one of the earliest white box attacks from EPFL University. To summarize of the presentation, first I'll talk about paper's objectives, then the Deepfool algorithm in more detail, which is first giving an example of adversarial images. Then I'm going to talk about some mathematical backgrounds, then Deepfool for binary classification problems, and then Deepfool for multi-class classification. And next, Marzi will talk about experimental results. And finally, we'll both talk about conclusion. All right, so about objectives of the paper, it's actually to propose a method to compute robustness to adversarial perturbations. It defines adversarial perturbation as the minimal perturbation that's sufficient to change the estimated label of a classifier. So if K is our classifier, K hat X is the estimated label for X, then K hat of X plus R should be different than K hat X, where R is an adversarial perturbation. Next, the paper defines robustness of classifier K in this case as the expected normalized adversarial perturbation over all images. So you can use this formula to compare two different classifiers in terms of robustness. Okay, now the Deepfool algorithm. Here we see an example of a whale and two adversarial examples. The first adversarial example is generated by Deepfool. And here you can see the perturbation. Next, we see an adversarial example generated by FGSM. As you can see, FGSM's perturbation is much larger than the perturbation found by Deepfool algorithm. Now, I can informally summarize the entire Deepfool algorithm in 6 steps. The first step, we linearize the classifier around the point of interest. Then we find the closest decision boundary. Next, we compute the minimal perturbation to this closest boundary. Then we update our current point. Next, we go back to step 1 if we didn't already reach the boundary. And finally, we return the sum of all perturbations found in step 3. Now, in the previous slide, I talked about a few steps that need more clarification. Specifically, how do we linearize a classifier? How to find the closest decision boundary, and how to find the minimal perturbation. So we'll see the answer to these questions when I talk about mathematical background in the next slides. For the first question of linearizing a classifier, basically we use first order Taylor series. So the first order Taylor series of function fx around a is defined as fa plus x minus a times derivative of f at point A. Now, generally our classifiers have several variables. So the function is actually a multivariable function. In that case, in Taylor series, we basically exchange derivative of f with gradient of f. And we also replace a and x, both of them are going to be vectors now. It's also worth mentioning that Deepfool for binary classification is equivalent to Newton's method for finding roots of a function. Newton's method also iteratively linearize the function and find a better estimation. I mean, this formula is the same as what we use in Deepfool, basically for binary classification. Another part of mathematical background is how can we calculate the distance of point x from hyperplane wx plus b? As you can see here, this is the formula to calculate that distance. And next question is, what's the vector that projects x0 onto the hyperplane, this hyperplane? And this is the formula for that. Both of these formulas are used in the Deepfool algorithm. All right, so here is Deepfool algorithm for binary classification. In this case, there is only so in this case, there is only one hyperplane. If the classifier is already linear, we just find the minimal perturbation and find the distance. Okay, yeah, so if the classifier is already linear, then we just find the distance and there is no iteration. And the method is exact. But if the classifier is not affine, it's not linear, then we have to do the iterative procedure that we just mentioned. So as it is shown here in the second figure, the classifier is a wired frame graph. We first linearize it at point x0 and f of x0 to get to this green plane that you see here. Then we compute the distance of x0 from the orange line, which is the decision boundary, which is basically where this green plane is equal to 0. And that gives us, brings us to x1, the next solution basically. And we can repeat this procedure several times to get to better solutions. Once we pass this decision boundary, then we found it, the perturbation, adversarial perturbation. Now for multi-class classification, we can transform the problem into several one versus all binary classifiers. Again, we linearize each classifier if it is not already linear. The major difference is that we have several hyperplanes and need to calculate the distance to all in order to find the closest boundary, basically. Here we see like a general multi-class classification. If it's not linear, we should actually change each of these boundaries between two classes to a hyperplane. And then we basically, for point x0, we'll find the distance to all of these hyperplanes surrounding it and finding the closest hyperplane and doing the same procedure as we have seen before. And here we see the final version of the algorithm. It iterates as long as the estimated label is not changed. Here it finds the decision boundary between estimated class and all others. And then here it finds the closest basically hyperplane and the distance to that basically hyperplane. It's gonna update our current solution. And after we do enough iterations, we will basically return the sum of all the perturbation as the adversarial perturbation. Okay, so now Marizy will talk about the experiment section of the paper.
Okay, good afternoon, everybody. We'll start off the experiments by explaining the data set and model architectures that have been used in Deepfool paper. They have used two pre-trained models for MNIST, namely 2 layers of fully connected network and 2 layers of LeNet architecture. For CPAR10, they are using 3 layers of LeNet and also a network and network architecture. And for ImageNet dataset, they are using pre-trained models of CAFnet and GoogleNet. In the first set of experiments, they compared the adversarial robustness of different classifiers using average robustness metric, as it is defined here. So the adversarial robustness of a classifier F is basically the average of the ratio of norm of the minimum perturbation over the norm of the image uh, for all the samples in the test dataset. We see here the result of this comparison for Deepfool with two other methods. This one is fast gradient sign method that actually adds a small perturbation to the image based on the sign of the gradient of loss with respect to the input image. And this one is computing the minimum perturbation based on solving a series of penalized optimization problems. As we can see for and this column is the test error rate for the classifier. We see that for the Deepfool model, it is significantly faster than this optimization based problem here, and it's uh, generating significantly a smaller perturbation compared to fast gradient sign method. Actually, the perturbation is 5 times smaller than fast gradient sign method. We have the similar result for CFAR10 models in terms of the magnitude of the perturbation and also the speed of computation. For the ImageNet dataset for GoogleNet, we see that the Deepfool generates 25 times smaller perturbation compared to um, fast gradient sign method. In the next set of experiments, they evaluate the effect of fine-tuning a model based on the adversarial samples on adversarial robustness. So to this end, for each model architecture, they fine-tune that model for 5 more epochs on adversarial samples generated by Deepfool here in the blue curve and fast gradient sign method. And also they continue to train 5 more epochs based on clean sample to have a fair comparison. Here we have the comparison of the performance, like the adversarial robustness for MNIST dataset, and we see that fine-tuning the model based on the Deepfool samples, adversarial samples, improves the adversarial robustness by 50% compared to clean model for both architecture. Uh, but it reduces the adversarial robustness when we fine tune the model based on fast gradient sign method. For CFAR10 dataset, we have similar observation for Deepfool method, and it improves the adversarial robustness by 40% compared to uh, clean model. Here we have clean model, and this is the Deepfool model. But again, we see that in 3 cases, the out of 4 cases, the fine tuning the model based on the fast gradient sign method adversarial examples reduces the adversarial robustness. So they hypothesized that the large magnitude of fast gradient sign method perturbation is the reason for the negative effect of that on the adversarial robustness. To verify that, they are actually fine tuning a model based on the magnified Deepfool perturbation samples. with different scales. We see here in the different scales of the model, and they compute for each at each epoch. They compute the adversarial robustness, the average adversarial robustness, and we see that the larger the magnitude of the perturbation that becomes here with a scale of 3, the average adversarial robustness of the model decreases. So they conclude that the fine-tuning a model with overly perturbed samples negatively affect the model because the large perturbation actually changes the model. Here we see the examples generated based on the different scales of uh, Deepfool perturbation. For the largest scale, when the alpha is equal to 4, the sample is actually similar to digit 7, and during the fine tuning, we'll label it as a 1. So it's basically a wrong uh, sample and label correspondence that leads to the negative effect of fine tuning on the uh, adversarial samples generated by fast gradient sign method. And here we see the effect of fine tuning on the performance of each model. So we have Deepfool that consistently improve the performance of the model and reduce the error rate compared to clean models. But for fast gradient sign method, it decreases the performance and increases the error rate compared to clean models. Finally, they show the importance of a correct estimation of the minimal perturbation in judging adversarial robustness. To this end, they fine-tune NIN model for 5 more epochs based on the fast gradient sign method adversarial samples. Then they evaluate average robustness based on the Deepfool and fast gradient sign metric. As we can, and then they normalize the uh, computed adversarial robustness based on the original robustness of each network. As we can see here, the fast gradient sign method exaggerates on the robustness of the fine-tuned model, and it shows the importance of finding the minimal perturbation and using that for evaluating the adversarial robustness and comparing the models. And we have now conclusion for this paper.
Now I'll talk about the strengths of the paper. First of all, it's a simple and accurate method for computing adversarial perturbations and comparing classifiers. Second, can it, second, second, it generates a smaller perturbation than FGSM. Third, it's the experiments in the paper show that it's more effective for adversarial training than FGSM. Another advantage is that Deepfool extends norms to different LP norms. Um, Another plus for the paper, in my opinion, is its extensive experiments with different architectures and different datasets. Next positive is existence of exact solution if you have linear classifiers. And now Deepfool can also be thought of as a variant of the well-known adaptive size gradient descent optimization. Finally, it's faster than other state-of-the-art methods proposed by the time of this paper's publication.
Okay.
So against this paper, so the Deepfool algorithm is not guaranteed to converge because it's an optimization-based problem. Second, the magnitude of classification confidence is not considered in the computation of the minimal perturbation. The third disadvantage is that Deepfool is a greedy algorithm. It means that it does not necessarily converge to the minimum perturbation. And finally, this is more of a suggestion that and continuation of this work because Deepfool use only first order approximation of the model classifier. What if we use higher order of approximation like second order? And so yeah, that's the disadvantages of Deepfool in my opinion.